right, welcome back. This is Unit 5.2. In this section, we're going to talk about types of bonds, and this information can be found in chapters 7 and 8 of your textbook. We've talked a little bit about this, but we're going to review that. So different types of bonds. There are 3 different types of bonds that we're going to need to know for this section. Before we talk about those, let's review. All matter is composed of atoms. Okay. Atoms are what are on the periodic table. Atoms join together to form compounds and molecules, and this joining together is what is called or referred to as bonding. So our first type of bond that we're going to review are metals bonded to nonmetals. So if we look at the periodic table, let me just drag this over. Remember, metals and nonmetals are separated by the stair-step line that goes down through the right side of the periodic table here. So all of these on this side, these are considered to be the metals of the periodic table. And then all of these on this side, these are the nonmetals. Okay. And ionic bonding is when you take one of the elements, one or more of the elements from the metal side, and it bonds with one or more of the elements from the nonmetal side. Okay. We refer to that as ionic bonding. And the next bonding that we're going to talk about is between nonmetals and nonmetals. So again, this is covalent bonding. This is when they're sharing electrons. So we're going to take 2 representatives from this side of the periodic table, and they bond together. Okay, 2 nonmetals is covalent bonding. And then the last bonding that we're going to talk about is metallic bonding. Metallic bonding is 2 atoms from the metal side of the periodic table. And it's usually the transition metals and the inner transition metals right here that bond together to form metallic bonding. We're going to talk about metallic bonding too much, but we will talk about it some, and then I'll continue to bring it up as we start talking about other things in chemistry. All right, so there's ionic bonding, covalent bonding, and metallic bonding. So let's concentrate on ionic bonding here for a second. Now, ionic bonding happens more often between metals that are in group 1 and 2 and nonmetals that are in group 16 and 17. Not to say that it can happen with the others, but more often it's between 1 and 2 and 16 and 17. And remember, metals lose electrons and nonmetals gain electrons. Now, this creates charged ions, and it's these different charges that cause these ions to be attracted to each other, because remember, opposites attract. And this attraction that they feel between each other is called an electrostatic attraction. So let's take sodium, which is group 1, and chlorine, which is group 17, as an example. Sodium is a metal. It's got 11 protons and 11 electrons, okay? And it's a neutral atom. So 2 electrons in this first orbital, and then 8 electrons in the next orbital, and then just 1 electron in this outer orbital here. And so it really wants to have 8 valence electrons. So it wants to lose this 1 valence electron that it currently has. And when it does lose this electron, or to give this electron away, it still has 11 protons and then just 10 electrons now. And so that giving away causes sodium to have a +1 charge, because the 11 protons are still present, and those charges are canceled out by just 10 electrons. So we still have a +1 charge left over. Okay, so this is the sodium ion. Now, at the same time, chlorine, it has 17 protons and 17 electrons, 2, 8, and 7. and it wants a full valence shell. So it really wants to gain this one valence electron. And when it does, it still has 17 protons, but now it has 18 electrons. So that gives it a negative charge, creating the chloride ion. And so when these two get in approximation to each other, the electrostatic attraction is going to take over, and they're going to snap together just like two magnets and form a bond of sodium chloride. Okay, and this just doesn't happen once with one sodium and one chloride ion. This happens many, many, many times. And so what you get is what's called a crystal lattice, where you have many sodiums. So sodium is represented here by this yellow sphere. You have many sodium ions that do this, that are attracted to many chloride ions that have gained electrons. So you have this 3D structure. That's called a crystal lattice. And when we represent a single bond of just the lowest whole number ratio of the cation, remember cations are positive and anions are negative. This is just a representation of one, what's called formula unit. And that's important. So make sure you write that down. One smallest whole number cation anion ratio of this big lattice is called a formula unit. All right, and there's many different types of ionic bonds, and they form crystals, and some of these crystals are very pretty and have interesting shapes. Here we see beryl, which is beryllium, aluminum, and a polyatomic ion called sulfate that we're going to talk about in our next section. This is barite, which is barium and sulfate. Okay, and then calcite, which is calcium and carbonate. This is wolfite. This is plutonium, molybdenum, and oxygen. And this is cinnabar, which is mercury and sulfur combined together. This is gross sulfurite, which is calcium, aluminum, and sulfate. And this is argonite, which is calcium and carbonate. You can see a lot of these at the Perot Museum. The Perot Museum has a very big collection of minerals, and the Perot Museum is in Dallas. They have on, I think it's the third floor, a very, very, very big collection of all these crystals, and it's really, really pretty. So if you ever make your way over there, make sure you go see that. All right, so to summarize ionic bonding, go ahead and pause the video and write these down. All right, ionic compounds form between metals and nonmetals, typically between groups 1 and 2, which are the metals, and 16 and 17, which are the nonmetals. Okay, there's a transfer of electrons from the metal to the nonmetal. An electrostatic attraction is established. Many ions form crystal lattice structures, and ionic formulas represent one single formula unit of the lattice. So when we write an ionic formula like NaCl, it's just a single formula unit of that much bigger lattice structure. All right, that's ionic bonding. Next, talking about covalent bonding. And like I said before, we did talk a lot about this in 5.1, but we're going to review it in 5.2. Covalent bonding forms between two nonmetals. So two representatives from the right side of the periodic table, on the right side of that stair step, those are the nonmetals. When two nonmetals approach each other, there's a push away because of the electrons, a repulsion. These negative electrons push away from each other. But at the same time, there's an attractive force between the protons of one of the atoms and the electrons of the other. So you have this push and pull. And so when these valence electrons in the outer shell start overlapping, then that bonding occurs because they start sharing those electrons and completing their octets. And that is covalent bonding. All right, so covalent bonding occurs between two nonmetal atoms. And I'm going over 1, 2, 3, and 4 that you need to write down. no electron transfer takes place. The attractive force between atoms is from the nuclei of one atom and the electrons of the other atom. And covalent molecules almost always exist as independent molecules rather than the large crystal lattices. So you can have a single molecule of, say, sugar or, say, carbon dioxide. Those exist as single molecules, which is different than ionic bonding. All right, polar covalent molecules. When we think about this word polar, we think about poles. And the best example is a magnet. A magnet has a north and a south pole. All right, and we use this same idea when we talk about some covalent molecules, not all, but some covalent molecules. Sometimes there's an unequal sharing of the electrons because, take for example, HCl. The chlorine in this bond is much, much more electronegative, which means it wants the electrons around it than hydrogen is. So chlorine is called an electron hog. Now the difference in this electronegativity between these two increases the concentration of the electrons around the chlorine, and it sets up what's called a polar molecule, where since electrons are negative, okay, and chlorine hogs the electrons to this side, we have a partial negative charge on this side because this is, even though this is a neutral molecule, the electrons are pulled in that direction, so it sets up a very small, slightly negative charge on this side, which leaves a slight positive charge on this side. Okay, and we use this lowercase Greek letter delta to signify a partial, not a whole positive charge, but a partial positive charge. Same thing here with the negative. This is a partial negative charge. And this is called a polar molecule. Some molecules don't do this. Some molecules are made of like carbon and hydrogen, like we saw in 5.1. Okay, so carbon is not that much more electronegative than hydrogen. So we set up a situation like this where the electrons are shared equally between all of these. Carbon is not an electron hog, so that's not polar covalent, but this one is. And so sometimes they'll represent it by doing this line where over here on the hydrogen, it's got a plus charge and the electrons are drawn towards the chlorine. Okay, so polar covalent. So there's non-polar covalent and polar covalent bonds. All right, and let's compare now the strength of ionic versus covalent bonds. Ionic compounds are usually solids at room temperature. Okay, so if you look on the periodic table, most of those are solids, but there are a couple that are liquids and there are many that are gases. But when they bond together, it changes the whole chemical characteristics of the atom. And so when you form ionic compounds, most of those that are formed are going to be solid at room temperature because they have very, very high melting points because of the electrostatic force that holds those two atoms together is very, very strong. So take, for example, sodium chloride. It has a melting point of 801 degrees Celsius, as opposed to sucrose, table sugar, which is a covalent molecule that has a melting point of 186 degrees Celsius. So you can easily melt sugar in kitchens to produce candies like caramel and Jolly Ranchers. All right, covalent molecules do not exist as lattice structures, so they don't have all of those molecule to molecule forces that are holding it together in a crystal. And so again, that lowers the melting point, where ionic compounds that have all of these big forces, not only inside the molecule, intermolecular, but intramolecular. molecular between different molecules, they also have those attractive forces. Okay, and another covalent molecule, methane, it melts. Now we think of methane as a gas, methane gas at room temperature, and it is. And methane is just one carbon with 4 hydrogens attached to it, and it melts at negative 182 degrees Celsius. Okay, so very, very weak bonds in here. So why is table sugar's melting point so much higher than methane? Table sugar is a polar covalent molecule and exists in a weak lattice called a network covalent solid. So table sugar, even though I think I mentioned before it's not polar, it's very, very slightly polar. So it's going to have a tiny little bit of attraction between different molecules. And so it's going to form sometimes some crystals, and we see that in rock candy. So if you've ever seen rock candy at the store, you see, and I have an example I'll show you, it forms crystals, but these are very, very weak. So that's why we see a melting point of 186 as opposed to negative 182. Okay. And here's some examples of some things that you can make because sugar does melt at low temperatures. You can take Jolly Ranchers and put them on like a cookie sheet or something and put a popsicle stick under them and let them melt in the oven, and they make like popsicles. And you could also take here cookie cutters and put peppermints inside the cookie cutter and then put them in the oven to melt them. And they'll melt a little bit and form shape, and people like make Christmas ornaments out of this. When you take them out of the oven, they get a toothpick and they like drill a hole on one end like this, and so you can feed a ribbon through there and then hang these on your tree. All right, so that's just some difference between ionic and covalent compounds. Ionic, very, very high melting points, where covalent molecules, polar covalent and non-polar covalent, very, very low melting points. All right, so that's it. Make sure you slap that like button right across the face. Give me a thumbs up and leave a comment.